was a lot of debate about whether or not this reaction is happening stepwise or all at once. And at one time, it was thought that this first reaction happens and then there's a second reaction. However, this is the current state of affairs. It's thought that everything is happening at one time. And this is known as a 2+2 cycle addition. So we'll stick with that mechanism for now. So let's try one more for practice. Let's go ahead and we're going to take, let's just say we have the Grignard reagent already made. Let's put a ring here on our ketone. And let's react this with, how about something that has a ethyl and a methyl group. And there's our ylid. And so I'll pause for a minute here. And if you take a second, and let's predict the reaction product there. And draw the mechanism, if you would, please, for that. So we'll stop for a minute for that. So as you're working through that, I think just like the top problem, it's easiest to make sure to have things lined up properly. I'm sure it's drawn much better on your notes. But I intentionally drew this above the arrow, but we could tilt this so that we can then think about mechanistically what's happening here, aligning the ylid with the ketone. So I have a methyl and an ethyl group. Down there's our four-membered ring intermediate. And then now let's form the carbon-carbon double bond and the phosphorus-oxygen double bond. So have that connect. And I think, actually, when I look back here, I called this triphenyl phosphorus oxide. It should be triphenyl phosphine oxide. So make sure that that's correct. All right, so we end up with this sort of a acidic product. So we formed a new alkene, a carbon-carbon double bond. So we could write the same thing here without the C, just make it a little bit more clear. So overall, what you might end up seeing would be, we would take here, notice something like this species, So it's chiral carbon, but that doesn't matter in this case. We would react this with PPH3. Followed by N-butyl lithium. Oops. I'll draw it here without the carbon, since sometimes we'll see it like that. Plus, minus. So that's our ylide. So the overall reaction, just like when we had to make a Grignard reagent, you take an alkyl bromide here and react this with magnesium to make the Grignard reagent and use that in a reaction of interest. Here to make the Wittig reagent, you first take your alkyl halide, react it with triphenylphosphine, generating this species here, followed by the reaction with N-butyl lithium. Now while we're at it, let's put in a little bit more detail. This reaction here with the N-butyl lithium is normally done in a solvent like ether. It's such a highly reactive species. And scroll up and put ether in that reaction now as well. And one more point here, while we've seen this now a little bit more, is again, this first step here, reaction with the alkyl halide, is an SN2 reaction. So notice here, it's methyl bromide, so not sterically hindered, great for an SN2 reaction. Down here, this species now that we generate this ylide, go over here to the right, this is a secondary bromide, so that's not as good as the methyl bromide. The primary would be even better. However, you will see secondary alkyl halides used in Grignard reactions, so methyl is best, primary followed by secondary. Turns out the triphenylphosphine is not a very good base overall, so we do not have to really worry so much about elimination reactions, but it's still, you want to follow the same reactivity trend that you have with an SN2 reaction. So now another complexity of the reaction is, notice here so far, we've used either a species, I'll circle this one on the bottom here, we're either at two hydrogens, or now in this case we have a methyl and an ethyl group. However, this ring, both sides are the same, so we do not have to worry about any stereochemistry. We don't have to worry about R and S and such, because this is an sp2 hybridized carbon. However, what if we have something like this ketone shown on the next page? And let's react this with, let's condense this down to this particular ylide. Let's put the positive charge here and the negative charge here. So now we're going to generate a new alkene. And let's actually write the mechanism down here below since we have space. I should make this part bigger. Ends up being the same size, I think. So PPH3 here. Now we'll have our carbon. Let's just put the carbon and put the alpha group dangling out below, and there's a hydrogen on the other side. Negative formal charge, positive formal charge. Let's form our four-membered oxyphosphatane intermediate. We have a hydrogen, and we have this ethyl group here. And then now this is going to collapse to form the alkene and the triphenylphosphine oxide. Okay. So now let's stand this part back up. So where we had the carbon-oxygen double bond here, we're going to put the carbon-carbon bond. So I'm going to kind of move this back up so it's in an easier way to see. By that I mean I'm going to put this here. So we have the methyl group here. And now on our carbon here, which is the carbon that we have right here of the alkene, we have a hydrogen and we have an ethyl group. So we could put the hydrogen here and the ethyl group here. plus, and if I can squeeze it in, could have the hydrogen on this side, and the alpha group over here. So in this particular case, we can generate two different stereoisomers. And going back to how we named the alkene, this first compound, this benzene ring is going to be the higher priority on this bottom side. This ethyl group will be the higher priority. So this one is going to be E, and this one will be Z. So if you can form stereoisomers, you will form a mixture. Or a mixture of E and Z. And we're not going to go into it, but it's actually quite complicated as to which one is going to be the dominant product or the major product. In the simplest case, it would seem like the E would be the major product because it's going to keep the two larger groups away from each other. However, a lot of times in these Wittig reactions, it actually is the Z product that is the major product. So it depends on the temperature of the reaction, the solvent, if you have electron withdrawing groups, lots of different things. All we're going to say for our purposes now is that you'll end up with a mixture of the E and the Z stereoisomers. So if you can form stereoisomers, you will, and you'll have a mixture of both. Okay, so the common trend here is we're taking a ketone or an aldehyde. Here was always just been a ketone. We can react this now with this Wittig reagent. General mechanisms we've shown here. We're forming an alkene in the place of where the ketone or aldehyde was, where the carbonyl group was. And now we first introduced a compound that has stereoisomers that can form. And if you can form stereoisomers, you do.